morning, Srini. Have a good sleep. How are you? Okay, let us make a start. Unless you got anything you want to ask, anything you want to ask? Anything not clear? Are you with me? Yep, ready to start? Why are you so quiet this morning? Too tired? Yep. Anything you want to ask or anything you want to talk to me about before I start? You are very quiet this morning. You are muted. You are muted. You are muted. Talk to me. Talk to me. Don't keep quiet. I don't know what is happening.
Hello?
Yeah?
Hello?
Are you with me?
Yeah, I'm with you, sir. Hello.
Can't hear you.
Hello.
Yeah? Speak louder. Can't hear you. Can you see the slide?
Yes, teacher, I can see. You can hear me now?
Yeah, can hear you now.
Okay.
Anything you want to ask? If not, let us make a start there.
Yeah, let's make a start, sir.
Well, as I said to you, the tuition will not help you unless you after tuition you go and try the different section in your revision book. I think your revision book is good enough to help you, except the weakness about you is you don't want to do homework. So you don't want to put your mind to work. I cannot work for you. Can I teach you only? Right? I'm doing well because I work through most of the question. So that's why I can so far don't have any problem, can solve all the problem. So you have to do that if you want to improve. So far you didn't do homework, that's why there is no improvement in your grade. Okay, today we go to gravitational potential. We're supposed to define what the gravitational potential at a point in a gravitational field, and we're supposed to derive this formula, then use the formula for potential energy, and then show that your change in potential energy equals to mgh, right? For special case near the Earth's surface, right? Special case of this one near the Earth's surface, and then use the relationship. Explain with graphical illustration the variation of gravitational field strength, gravitational potential with distance from a point mass. Okay, let us make a start. Right. So all this in reference to the Earth. Okay, let's define gravitational potential of this mass. This is the mass that we are interested in. You want to find the potential, right? Can use the symbol V. Some textbook will use phi. Right? So we are interested at this point. At this point, what is the gravitational potential? or the potential energy. Let's define. It doesn't matter about whether there's a mass there or not. Doesn't matter. It can be in any field. Essentially, we are interested in this point. And the potential is usually contributed by mass there. Right? Gravitational potential at a point is the work done per unit mass in bringing a point mass from infinity to the point. Right? We are bringing point mass of 1 kilogram from infinity to the point. That means we are taking this one at infinity. We consider the potential energy as 0 or the potential as 0. Right? We bring it to the point. Okay, the essential thing to remember is the force is attractive. So we don't have to do any work. The system, that means the attraction of this mass on this 1 kilogram will do the work for us to bring it to this point. So we are interested as a potential at this point. Okay, so the potential at infinity, we call it 0. And we are interested, the potential, if it's 1 kilogram, equals to the work done.
Go back to the previous slide.
Memory work only, nothing much. Learn to accept it and learn how to use it. You cannot question the scientists why they define it this way.
So it's W over M lah. So
If it's 1 kilogram, then it's equals to the work done. No? Negative because the force is attractive. So you don't have to do the work. The work is done by the system.
negative because the force is attractive and work is done.
Be a bit louder, can't hear you.
Oh.
Okay. The force is attractive. That's why you get a negative sign.
Work is done by the force is
by the system. The system is this mass there. This is the one that do the work. We don't have to move, bring it. Right? We don't have to do the work to bring it there. That's why it's negative. If it's done by us, then it'll be positive. We put into the system. Then that one is a repulsive force. That's for electric field lah.
Yeah, positive is for electric field lah. Okay.
Okay, so the potential, gravitational potential at this point, which we call P, is given by this value. You can put V if you want to, right? Because Gm over R, the negative sign must be there, right? If it's a vector, you don't have to worry because the negative sign shows direction. So you don't have to use negative sign in our calculation as long as we know the direction. Whereas for potential, the negative sign must be there. It shows that it is at a lower potential. Why is potential negative? Force is attractive, the first thing. And then we choose that the potential at infinity equals to 0 at this point. So work is get out or is done by the system when the test mass is moved from infinity to the point. So when we move this is a test mass, or this is the mass that we move from infinity to the point. Okay, work done by the system or work got out of the system. The system is the one doing the work, not us. So the further the test mass is from the point M, the greater is the potential energy. Right? So simple reason, infinity is 0. So as you go further, just like in a uniform field, the same thing. Right? You take it higher, greater potential energy. Higher still, greater potential energy. Same thing, same idea. Except we use a different formula.
So the further part is the positive force. I mean, it's positive, that means because it's further, what, right?
Just learn to understand this formula.
Correct.
Understand this formula, that's all. At infinity is 0. After that is negative. So the closer it is, the more negative it will be. That's all. We will draw the graph later that you can see it more clearly. Okay, so gravitational potential is just the potential energy per unit mass. Okay, unit joule per kilogram is a scalar quantity, so you don't have to worry about direction. Right, and then the thing to remember is the body, this body, right, or this body or test mass at higher potential energy will move to one with lower potential energy. Same thing, uniform field, the same thing. You take to a higher height, you move to the ground. You drop it, you go to the ground. Same thing in this non-uniform field. I said that non-uniform field, instead of choosing the surface as zero potential energy, we choose infinity as zero potential energy. That's our choice. That's why we get negative sign. Okay, so the negative sign must be there. Okay. Say a bit louder.
Can you explain again, sir? Sorry.
Okay. In uniform field, we normally treat the potential energy at the surface as zero, surface of the Earth. So it's the same idea, right? That means as you go higher and higher, the potential energy is going to be larger and larger. But in a non-uniform field, we choose infinity as our zero potential energy.
You mean further and further.
When I talk, you don't talk. I can't hear you. You want to ask when I stop talking. Okay? What is your problem?
No, sir. So further and further, only greater potential energy is it?
Same as uniform field. Potential energy is as you increase the height above the surface, the potential energy increases, become higher and higher. So it will be infinity. That potential energy will be infinity at a large distance away. Okay? But for non-uniform field, like right, the surface of the Earth, like a body, we cannot choose the surface of the Earth. So we have to choose infinity. So instead of infinity becomes large energy, we choose infinity as zero energy. So all the other energy becomes negative. Right? So the potential is basically the potential energy per unit mass. Sorry. Let me just adjust it slightly. Okay, there's a formula. Just understand the formula. Right? R is infinite, this is zero. And as R decreases, this one increases. That's what we are trying to do. And then we understand that gravitational potential per unit mass, that's our work done. Divided by mass is our potential. Unit, this is in joule, this is in kilogram, so it's joule per kilogram. It's a scalar quantity, so we don't have to worry about direction, and it's easier to calculate. Right? So same thing, you can have the same idea as a uniform field, same as non-uniform field. The higher the body is from the surface of the Earth, the greater is potential energy. So if the object is at higher potential energy, it will move to lower potential energy. Just like I draw a mass, it's high potential energy, it will go to surface of the Earth because the Earth is at low potential energy. Right? The negative sign must be there in the equation when you do the calculation. That's important to remember. Okay, anything else you want to ask? Okay, so you should be able to plot the graph, right, using the equation. If you are told at the surface, if the radius of the mass is r, and at the surface the potential energy is this one, that value, then you just put a cross there, right? 2r is divided by 2, right? That's why it's 0.5. 3r is divided by 3, so it's about 1/3. 1/3 is about here, 0.33. And 4r divided by 4 is about 0.25. Then your curve looks something like that. Sorry, my curve is slightly out. Maybe you can adjust it slightly. Okay, that's how you sketch if you are asked to sketch. Okay, that's how the graph look like. Right? That's how you sketch. Right? Surface, and the surface is pi 0, then you just half it. That's all. Right? Remember the negative sign must be there. Sorry that I didn't put a negative sign there. It should be there. You cannot put positive.
Negative sign must be in the equation.
Must be there. It's essential. Whereas if it's a vector graph, you don't have to be there. It's your choice. You want to put negative, you don't want to put negative, but it doesn't have to be there. Any comment?
No,
Okay.
so that means, as far as I understand, the equation must be negative, and then the high potential energy will move to the low one, right?
High potential energy will be higher and higher as you go further and further from the surface.
And you'll move to the low potential energy.
Yes.
Right.
Any object at higher potential energy will move to a lower potential energy.
There is no reason for that.
That's how you have been taught. Right? You can see, observe it. You don't believe it, you can observe it. Take your object to a higher height and drop it, it will come to surface of the earth. You have to accept that. You cannot simply question things that are fact. Yeah. These are things you have to learn last year already, and you are still asking the same thing. So that's your graph. Okay, sometimes some people like to draw it positive, but it should be negative. Right? But this is gravitational force in this case. So origin is at the center of the earth. The mass of the earth, the distance is small r. Sorry, that distance should be small r. Right? You just have to learn in physics, learn to understand, accept it, and learn how to use it. No point in every time question why this way, why that way. You won't progress. Right? It's just like math, you have to accept the formula. You cannot go and ask your math teacher why the formula is like that. Just have to the formula and learn how to use the formula. Right? So there's a force distance graph. Right? The force is attractive. So sometimes you put a negative sign there, but it doesn't have to be there. Negative sign, it shows that it's attractive force as all. It doesn't have to be there. Origin is center of the earth. So basically, that is the area, the work done. That's the work done. If you move from R2 to R1. So it's infinity, then this is the whole area. Okay, so we are now going to derive. It's in your book, page 134. Right? That's the derivation. That's how we define it. We move it from infinity to R. Right? That's your distance R, infinity to R. That's a small mass that we move. This is the one. This is the one stationary, or you can consider that at the Earth. This is the test mass. Okay, so if we change it to from R to infinity, we have to put a negative sign there. Okay, and then we remember our force is attractive. Okay, the distance is from the center of the earth. We move to the right, so we are taking to the right as positive. Right? Is remember we're dealing with vector, so vector to the right is positive. So our force is attractive, so that's why there is a negative sign there. That negative is because of this negative. Okay, this one is negative because this is negative. Then we can integrate. Okay, so integrate, there's this negative there. And then this 1 over R. Right? Now integration, there's a negative sign there. So in this case, our integrate from infinity will be 0. Then negative becomes positive, so we still got a negative there. That's why we get this equation. That's your integration. In case you okay. And this is our work done for mass M, but we define it as potential is work done per unit mass. So you have to find the work done divided by the mass that we bring. So that's why we get. Okay. Any comment?
Okay, so the negative you put it outside fine, and then the inside negative, what other negative for what answer?
This negative because of this integration. This negative because of this negative.
No. The other negative. I'm not talking about the outside.
Which negative? This one.
The negative GMM over R squared, that one. Yeah. The one inside one, not the outside
This one is because of that.
No. I'm talking about the other one.
This one.
Other one.
This one no
yes,
need to worry,
yes.
This one no need to worry.
Why?
You
You told
just show
reason
direction
now.
only. You just show direction only.
Direction. No, you say to the going to the right means is going positive, so going to the left means going negative. Is it?
Yeah, it's attractive force.
Attractive force, that's why going to the left lah. It's negative.
The
Going
force
to
is
the right
attractive.
means positive,
It's
not
going to the
negative.
left. Then you can see that. But we take origin as here, so our R is actually a vector. It's going to the right.
So it's not an attractive force anymore lah. It's a repulsive if it's going to the right.
Yeah, it's attractive force.
No. It's not an attractive force because it's going to the right. Right.
The displacement is to the right. The force is to the left.
I don't understand. What?
Okay? The force is to the left.
Yes.
The vector is starting from here to the right.
Yes.
There's your R. Yeah.
Yeah. Okay. Then.
Okay. Right? Don't worry about this negative sign there, because you want to get negative here. Okay. Any comment?
No.
Okay. Know how to use it lah. And know how to derive it. Right? Gravitational potential energy is the ability to do work as a result of its position in this case. So that's why, same thing, potential energy is just the potential times the mass that you bring. This is the mass that you bring. For mass M, at a distance r from the center of the Earth, the potential energy is just your potential times m. That's all. Right? This mass there, that's the Earth. The Earth has this potential. The potential energy of this mass there at a distance r away, you just multiply by this mass, that's all. That's the potential energy. Memorize it and know how to use it. That's the potential. Right? Potential here at a distance r from this big mass. And you put a mass there, the potential energy is just that. Okay, for a particle, example, a rocket of mass m, moving with velocity u from potential phi1 to phi2. That means this is the Earth. The Earth has a big capital M, the mass m. That's the distance from A, point P. So if your particle is here or the rocket is here, it has a potential phi1. Then it moves to phi2. Right? So it's the same thing. Right? There's a mass there at point P. It has a velocity u, initial velocity. And then it moves a small distance, delta r, to delta r away. It has a velocity v. Right? Same. You just think about uniform field. When you throw an object up, the velocity decreases. Why? Because the force is attractive. So you can use the same idea. Right? It's going to lose kinetic energy. Where does it go? We must gain potential energy. But you cannot use the formula for uniform field. Right? So there is the loss in kinetic energy. Potential energy is m. Right? This is larger. This one is smaller. That's why you take your larger minus the smaller one. Phi2 minus phi1. U is the initial speed here. V is the final speed at this level. So here, the particle is moving from lower potential energy, which is here, to higher potential energy. Okay. For uniform field, you consider this as MGH. Right? This one as MGH. That's all. So you have to readjust your thinking. Okay, any question? Okay, let's carry on.
Wait.
We move from a lower potential, this one, to a higher potential. So potential energy is just that one. That's the potential energy at this one, which is higher, minus the potential at the lower one. This is smaller. That's why we subtract.
So usually it's from high to low, but this time it's low to high. That's why the kinetic energy.
Same as uniform field. You throw a ball up, it moves from a lower potential energy to higher potential energy. That's why the kinetic energy decreases.
But lower to higher need more work done. What?
The work done is converted to potential energy.
That means it can be from anywhere lah, from high to low or low to high lah.
Yeah, it doesn't matter as long as you know how to calculate.
Oh, okay.
This is for a rocket shooting up.
Yeah.
And you can have one going down.
To low potential to high potential.
Right? It can be at a higher potential energy. It can be at infinity. And then it's dropping down to a point P, lower potential energy. So you must know how to calculate. Same idea. Right? Object M. That's the object M. Moving from rest. Right? Zero initial kinetic energy, initial speed or kinetic energy at infinity towards the mass M, a distance r away. So the velocity is lost in potential. Remember, higher is higher potential energy. So
Yes.
move to a lower potential energy. So it's a loss of potential energy, is gain in kinetic energy. Okay, so this one is 0. So that is a higher potential energy. It's just your phi times your mass, that mass that you bring down. And then this is the loss in kinetic energy. Initial one is 0. Okay, let's look at the relationship between potential and electric field strength. That's your electric field strength. Right? That's your big mass, the Earth. That's your point P. That's your distance R. That's your dr, a small distance away. So your gravitational field strength equals to minus gravitational potential. There. Right? It just basically you differentiate this one. You get this formula back. No? That's what this is telling you. And if it is a phi R graph, right? That's your distance graph R. Then remember, is this equation tell you is a tangent to the curve, right? Tangent to the curve. Okay. Know the mass, understand the mass, and know how to interpret it. That's the origin here. Okay. Okay, if no question, let's carry on doing some questions.
Potential and field strength. So potential is the first formula, field strength is the second formula. The R
Yeah,
square one.
you just differentiate this one. You will get that one.
Wait, what? Again?
Yeah, this one. Look at this equation. This equation tell you are differentiate this one. Then you get this equation.
Oh, you differentiate the potential one, you get the field strength one lah.
Yeah, you get the field strength, you differentiate the potential formula.
Okay.
Right? At any point in the gravitational field G, you can call any point your P. G points towards the mass. Right? As I said, G is always attractive. It's always point towards the mass there. If the displacement is away from M, like this one, right? You take it to the right. The displacement and G are in opposite direction. Right? If you take it to the right, your displacement is moving to the right, but your G is going to the left. As R increases, potential increases. That's important to remember because we treat infinity as our highest potential as 0. So as you move further and further away, the potential will increase. That's shown by the negative sign. This is larger and larger. This one becomes smaller and smaller. Right? Let's just derive the relationship. G is the force per unit, just to show you help you to understand. Right? That's your G. That's our definition. And then there's our definition for potential. Work done divided by mass. And work done, we have defined as force times displacement. Right? Remember, when we define it, the force and the displacement are in the same direction. That's why we didn't bother about the negative sign there. They are same direction. But in this case, the displacement is going to the right, the force is to the left. Right? So that's the reason why we put a negative sign there, because the two are in different direction. Not like our definition here. Right? They are in the same direction. So that's why we get our minus F dr. So when we take our minus dr across there, we get this equation. Right? So we can expect, right? We just divide this by m. Divide this by m, then we get our G. Right? divided by M. Force divided by M, you get G. W divided by M, you get 5. Right? Put that one there. Right? Because you can take cross multiply there. 5M. Then take this one across there. GM. Don't need to worry if you find it confusing. Right? Just memorize the formula and know how to use it. This is just to help you in case you want to relate to what you have studied.
So back again, sorry. So that means the W equals to negative F R is interlinked between two formulas, right? That's it, right?
R is negative because your force is attractive. It's moved in a different direction from the vector delta R. Right? This is delta R or dr. It move upwards. This one move downwards because this is attractive. That's why we got a negative sign there. Normally, our force and displacement are in the same direction. That's why we get positive when we study work done. Okay.
Yeah, continue.
Okay, at the surface of the Earth of radius R, that's the Earth, radius R, mass capital M, potential energy of a mass M. When you put a small mass on the surface of the Earth, you must know that is the potential energy. And you can differentiate it. You get this equation. A change in potential energy, a small distance. So you can take a small distance delta R above the surface, or dr, same thing. Right? Both mean the same thing. Small distance above the surface. Right? Then you take your dr across there. You get your small change in potential energy, small change above the surface of the Earth. Then your gm over r squared, that one, you can replace it with g, small g, gm r squared. Then you get your mg delta r. Right? This is your g, there's your m, there's your delta r. Right? Delta r usually we call it height, height above the surface. That's your height. There's your delta r. So we can rewrite it as that mgh. If our delta r is h is just a small height. Right? That's for uniform field. Okay. Now we do some calculation. Right? All this you need to know. All this. Right? That's the for yesterday we studied that. This one also, this formula. Now these two extra formula. Now to use it, know the graph. Right? What does the gradient of the graph represent? That's the gradient of the graph. Okay. Same thing. This one just a summary of the things that you need to know. Okay, it's just a relationship there. We've gone over that. Don't bother about all this. Test yourself. What's the answer for this one? Which of the, it's in your book. Right? It's just I want to review with you. Make sure you know, understand what's happening. Which of the following graph show correctly the variation of gravitational force on a point mass and the gravitational potential energy with distance r from the Earth? Yep. Yep. What is the answer?
Yeah, wait a minute. A.
No. It should be C. Okay. Square it becomes smaller, more negative. Right? Here they treat the force attractive as negative. That's why you get this one. Right? If you don't worry about negative sign, this one also wrong.
No, which one? Okay. No, which one?
Where?
F equals to which one is 1
F
over
is
x?
x
Which one is
square.
1 over x square?
This one is your, you must know the formula. Basic idea is must know the formula. Must know this formula. And you must know this formula. Right? You must know these two formula. There's a force formula. There's a potential energy formula. Right? You can use U if you want to. That's all. So that's why I work it out to help you see. Yes, as long as it's greater than 1, you can treat that as your radius or distance, R. Right? X square is decrease faster. This is your x square. That's your force. Decrease faster. Decrease faster. Yeah. What's the problem? This is your maths problem. You need to know how to draw the graph.
Understood, sir. Understood. Yeah, understand, sir.
Okay now.
Yeah, okay.
Okay, try this one. The distance between a body A, that's a body A of 8,000 kilogram, and body B 6,000 kilogram. Right? That distance there is 0.25 meter. Calculate the gravitational field strength due to two bodies at point P. That's your point P. With distance, this 0.2 and 0.15 from B. Okay, you can calculate now. Remember, it's a vector. I've shown you the direction of the vector. So go and calculate your resultant field strength. Can? Just use this formula. There's a formula. This formula. Right? No need to worry about negative sign because you already shown the direction. Potential one, use this formula. Right? Just draw on the diagram there, the direction. Right? This point P is the G is moving, is pointing towards A. At this point P, G is pointing towards B, that's all. And the two are vectors. Can? What's the answer? Can or cannot? If not, I show you the answer.
Cannot.
Okay. Right? This one, GA. Use this formula. Don't need to worry about negative sign because you already show the direction. That's the most important thing. Right? G is that one. Get from your data sheet or your constant. And then mass, that is your mass. Distance, 0.2 square. Calculate out. And calculate this one. Field due to body B. Same thing, same formula. Except know how to identify the R and the M. Right? That's your capital G. That's your mass. Right? This is your mass. R is that distance. And calculate out. Now you got the two value. Right? And then the other key is to remember. This is like 3, 4, 5. That means this is 3. Right? This is 4. So this is 5. That means this is a right angle triangle. This one. This is right angle. Right? I can use this parallelogram rule to calculate, or I can use triangle rule to calculate. That means this is my GB. Yeah, GB is here. Okay, it's a right angle triangle. So I take my common factor, 10 to the power minus 5 out. Then it's just GA. GA is this square plus that square. And calculate out. Okay. So you may have to calculate the direction or show the examiner the direction. That means you have to calculate this angle. This angle, because it's a vector. Vector must have a direction. But your book didn't give any direction, which is wrong already. You should calculate the direction. Okay. Any comment or anything not clear? This one is a right angle triangle. This one. So this one is saying, right? You write this is 3, this is 4, that is 5. Can anything not clear?
Okay.
Right? Calculate the next one. B, potential at point P. This one you don't have to worry about the direction. You just make sure the negative sign is there when you calculate. You just add the two potential. Calculate the potential due to this mass. Calculate the potential due to this mass. Right? As I say, that is a formula that you should use. Right? That is a formula you should use now. Calculate. So have a go. Can?
No, I just cannot.
You're not putting in effort to learn. That's all. Basically applying the formula only. This formula. To that mass there. You call it VA, potential. Then calculate out. Put your G value in. Negative sign is there. That mass is 8,000. That R is this distance. And after that, calculate for this mass. Potential due to this mass. Right? We call it VB at this point. Negative sign must be there. Sorry. I lost my negative sign. Negative sign must be there. This one. Important. And just put in your value. That's your G value. That's this mass. And 0.5, 0.15, then calculate out. And remember, it's a scalar, so you just add them up. Resultant potential, you just add this value plus this value. Right? Both of them are negative, so you get a negative answer.
Wait, resultant potential y minus answer.
This is minus. I'm just adding these two together, that's all. Because they are negative,
addition
negative there.
Or just adding. Okay.
Just add them up as a negative. If it's negative, you cannot change the answer. So get a negative value. It should be a negative value anyway. Okay. All right, try this one. P and Q. There's your P and Q. 2 points. A distance x away. Right? They don't have to show you the diagram. You are supposed to be able to draw your diagram. I just draw a diagram for you to see. Right? Where your x is greater than your r. R is the radius of the Earth. And then Q is 2x from the center of the Earth. Gravitational potential at P is given you, that value. What is the work done to take 1 kilogram mass from P to Q? Right? What's the work done? Yep. Can?
Void.
Cannot. Let's go to the answer. Right? We're just using this formula. Vx equals to constant.
Where you get Vx from, sir?
Vx is from this formula.
Oh.
Instead of 5, I use V. Then I didn't bother about the negative sign there, but I remember it must be there. Just to simplify my calculation, that's all. Okay. You are told that what's the work done? Right? What have I done? Vx. Distance is 2x. This distance is x. Oh, what I did was let me just try another step for you. In case you are a bit lost. Let's just write this step for you. I'm just using that equation. VQ. I'm just taking this is your V. Take the R across there. Not worry about negative sign there. Right? So VQ times your RQ? RQ equals to right now the other side is just the same thing. It's just now change to P, that's all. Right? Instead of Q there, I put a P there. That's all. Right? Now one VQ, I take the RQ down, VP. So that's your VP. Right? RP is X. RQ is 2X. So cancel my X. This is my half. And then I got my VP. Right? VP is just that one. So VQ is minus 400. Okay, it should be correct. Then after that, I want my potential energy. Right? Higher potential minus lower potential energy. So mass is 1. Right? That's your 1 kilogram that you move. M. And your VQ. Right? That's your VQ. VP. That's your VP. That. Right? The negative, the negative. Then we get a positive value. The answer is A. Okay. What is the answer for this one? The graph on the right shows a variation of gravitational potential with distance x, that's a distance x, from the center of the planet. What does the gradient at point P on the curve represent? Okay, what's the answer?
Boy.
No. Oh yeah, you are right. Boy, correct. Good.
Derivation.
Okay, this one you can go back and do your book. I've shown you it now already. Let's do a little bit of satellite motion. Yeah, getting a bit slow already. All these things you have learned in your first term and then you forget everything already. So I'm just like teaching you afresh. Okay, we have just covered only these 3 topics. Now this we are hoping we can do a little bit of this one. And then if you want, we can cover the rest on Monday. And we got time, we go to the static. Satellite motion in circular orbit. Solve problem involving satellite moving in circular orbit in gravitational field. Explain the concept of weightlessness. Right? Satellite motion in circular orbit. Circular orbit in inverse square field law. Right? That's the alternative term we use. Example, satellite moving, orbiting the Earth. Right? These are all satellites in circular orbit. Satellite can be natural, there's the moon, artificial, man-made. Right? Like this one, it can be a moon, or it can be artificial. Right? Or it can be Earth orbiting the sun. Right? This can be the sun. This can be the Earth. Right? So there are situations that we can apply. In this case, circular orbit or inverse square law. Okay, so that is your equator. That's your satellite. There's your polar orbit. There's your equatorial orbit. Orbit must pass through the center of the Earth, as the mass of the Earth is concentrated there. Right? Mass is there. That's why the orbit, right? The center of the orbit must pass through the Earth, whether it's this type of orbit or that type of orbit. We're not interested in this one. We're interested in this one. Motion of satellite in circular orbit. Consider a satellite of mass m, right, small m, moving in circular path or radius r around a body of mass capital M, and the speed of satellite is v. Right? You can draw that. There's a big M, and mass of the body or the Earth, and there's a satellite. That's the orbit radius r. That's your satellite, smaller mass m, and that's the speed v. Right? That's what we are saying. So there's a centripetal force. Right? Remember, it's moving in a circle, so there must be a resultant force there, and we call that resultant force centripetal force. So centripetal force is provided by gravitational force. Right? We know there's a centripetal force. The centripetal force must be provided by the attractive force between the satellite and the Earth. Right? Remember, that's our assumption. This body is a uniform density. Then we can consider as a point mass. Right? So essentially, gravitational force equals centripetal force. Gravitational force is Gmm over r square. Centripetal force is mv square over r. Right? Cancel our small mass m and cancel our r. Then rewrite our equation. V square Gm over r. Right? So that's the speed of the satellite is dependent on the mass of this body, right? Which is dependent on the mass of the Earth. That's the satellite. And the radius of the orbit. Right? Understand the formula and what does it mean? It doesn't depend on the mass of the satellite. Remember that. Right? Does not depend on the mass of satellite.
So go back to the previous slide, sir. Five. Before.
Kamu.
Okay.
Okay.
The orbit must pass through the center.
Can't hear you. Speak a bit louder.
The orbit must pass through the center of the Earth as the mass of Earth is concentrated.
Because the mass of the Earth is at the center there. That's why it must be the center of this orbit.
Because the mass of the Earth is there. For the orbit to move. Okay.
We don't think of the Earth as a big object like that. We think of it as a point mass at the center there.
Okay.
That's all. That's what we are doing.
So centripetal force is given by the satellite, right?
As long as it's moving in a circle, we know that there's a centripetal force exists. And the centripetal force is given by the mass and velocity square divided by r square. As long as it's in a circle, but we don't know what provides it, that's all. So in this case, it's the gravitational force that provides the centripetal force. That's why we are saying here. And we use it to calculate the formula for velocity.
So that means in order for speed of satellite to occur, it needs to have centripetal and gravitational force.
As long as any object is moving in a circle, it has centripetal force. Okay. And what provides the centripetal force is the gravitational force. That's all. That's what the equation is saying.
Okay.
Yeah, that means if there is no Earth there, no this big mass there, then it cannot move in a circle. It will move a straight line.
And then there's no centripetal.
If there is no mass there, it will move in a straight line. That's Newton's first law. That's all.
The one you say does not depend on the mass. Which one, okay.
So you must look at this equation. Right? Look at this equation. What does this equation tell you? It doesn't depend on the m, the small m, which is the mass of the satellite.
The
It
big
depends
M,
on the mass of this one, and
the
depend
body
on
speed.
the radius of the orbit.
Mm.
That's the speed of the satellite.
Yeah.
Okay, then we take a square root and where we get this equation. I just redraw the diagram for you, that's all. It's related to the Earth. Right? So the equation allows us to calculate the speed if we know the mass of the Earth and the radius of the orbit. Right? And then know how to see the equation. Mass of satellite is not in the equation. Right? That mass there is not in the equation. So it means the speed doesn't depend on the mass of the satellite. Right? So understand that as your radius decrease, as that radius increase, right, this one becomes larger, this becomes smaller. Or if this becomes smaller, the speed becomes larger. Right? That means further and further away, it will be at a lower speed if the orbit of higher radius. Can? Right? To calculate period, as I say, you must go to your circular motion. That's the equation that we have derived. There's a setup again. So to remember the speed, remember it's your distance divided by time. So you choose the distance as the circumference, then the time is the period of the satellite. So now you replace this one, your V with this one, which is 4 pi square r square t square, which is this one. This one is still the same. We are interested how the period and radius changes. So we replace that V with that one there. And we cross multiply, take the R across there, take the 4 pi square down. Okay, so we have shown that R cubed over T square equals to GM over 4 pi square. That means if you treat that as your sun, that as your planet, then R cubed over T square is a constant. That's the mass of the sun. Can? Anything not clear? Okay. Refer to your note, review it. Okay, so we can apply to our solar system. Right, remember, this is deriving from theory, Newton's law of universal gravitation. We show that R cubed over T square is constant. Of course, as scientists, we want to know, is it true or not? Apply to different planet, distance, and the period of planet that we can measure the radius of the planet from the sun. We can measure. Right? This is our original idea. This is the wrong idea. Right? This should be the sun, and then the Earth should be after Venus. Right? It's just for you. Exciting to see whether you can pick the mistake. So that's what Kepler did. Right? He measured the radius of the orbit and the period of the orbit and show that this is constant. Right? That's what he calculate. That's the measurement. And then show that it's constant. You can see quite constant. right? Slight different the value, but other than that, it's quite constant. So we are confident that Newton's law is okay, right? It's true. It's true, even though it's true because they are far apart. So we can consider the sun as a point mass. Okay, we have derived the formula. So how to calculate the kinetic energy of a satellite of mass m and m at a distance r away from the big mass? Yep. What's the answer? We are just using this equation, that's all. That's why we calculate. So now we want to calculate the kinetic energy of this mass. That's all. Kinetic energy of this mass. This is the equation that we get. Okay. So we just use our normal kinetic energy formula of mv squared. That's your v. Put inside there. That's our equation. Right? Either you memorize it or you derive it. It doesn't take a long time. Okay, calculate this one using the formula that we have derived. Right? Calculate the speed of the moon. You should be able to get 989 meters per second. And then you should be able to calculate the mass of the Earth. Have a go. Using the formula that I've derived for you. Right? Change this to second. Right? Radius of the Earth is given you. Change it to meter. Right? Change your period. 1 day is 24 hours. 1 hour is 3,600 seconds. Right? Convert to second. And right? Your speed is your 2 pi r divided by t. That's your 2 pi r. Right? Remember, this is the radius of the Earth. They are told is 60 times. So 60 times radius of the Earth. Your t, that's your t. Calculate that as your speed. And use this formula. Right? You already know the speed. You know that one. 60 times that. G, you constant. You can look up your table of constant and you can calculate your mass. Right? Rewrite your form. Yeah, you can write your whatever is given. That's your G. The G. That one is 60. And that. Change it to meter. Then the speed is 989. And calculate your mass. Yep. What's the problem? Can? Right? That's observing the Earth. Artificial satellites have a variety of uses. Many are used for making observation of the Earth's surface for commercial, environmental, meteorological, and military purposes. You want to spy on a country, what they are doing. Others are used for astronomical observation. Right? You can put a telescope there and observe about the stars, the galaxy. Right? That's how we benefit because there is no atmosphere when it's outside the Earth. Others are used for navigation, help us to move around in the ocean. Telecommunication, right? Send messages from one place to another, or broadcasting. That's the uses of satellite. Right? So we need 3 to cover the whole Earth. Right? Because 1 will cover only 1/3. 1/3. We need 3 to cover the whole Earth. Then geostationary orbit. geosynchronous orbit or parking orbit, depend on the book you use, but this is more common, geostationary orbit. So a geostationary orbit, satellite move in equatorial orbit. Right? The orbit is around the equator with a period of 24 hours. That means the same as the rotation of the Earth. And then move from west to east. So what is happening? The satellite remains directly above the same point, above the Earth's surface. Right? That's why some people, some book will call it parking orbit. It's just like parking your satellite above that, above the same point, above the same point on Earth. Right? That's the purpose of geostationary orbit, to observe what is happening. It's always there, of transmission of radio signal, or television signal, or internet signal. In this orbit, the Earth, right, is moving at the same rate as the Earth. That means it has the same angular velocity, omega, as the Earth, or same period as the Earth, same t. Either one, same omega or same t. So you must be able to tell the condition, right? Rotate from west to east. That means same direction as the Earth's rotation. Period of rotation is 24 hours, same as the Earth. Right? And above the equator. Right? We won't bother about this one. This one is for other useful purposes. So the orbit is quite large. Right? Orbit we can calculate out. So these are the uses there. Right? We won't bother about too much of that, just to. So energy is not mentioned in syllabus, but just go over that with you. For satellite of mass m, right? That's satellite. Mass m, small m, moving with speed v, radius r away, and the Earth is capital M. Okay. Total energy is potential plus kinetic. Right? Gravitational potential is just there. Potential energy is just times m, right? Mass of satellite, that's all. You get the potential. So we got that. Right? We have derived the kinetic energy, the speed of the satellite. So from there we can calculate our kinetic energy. Right? There's our kinetic energy. And these two combined. Place the v square with that one there. And that's the potential energy. So we just add them up together, the two, to get our total energy at a particular orbit. Okay. Minus gmm over 2r. Right? This one don't bother the relationship. Just know how to derive this, good enough already. And we draw the graph. That's the kinetic energy, positive. Total energy is lower. That's your potential energy. So if that's our starting orbit, when satellite move to a lower orbit, here, that's a lower orbit. That one. Right? If we draw graph, easier to see. Lower orbit, r is smaller. R is smaller. Right? The speed increases. Yeah, or kinetic energy increases. Potential energy decreases. Yeah, become more negative. Total energy also decreases, become more negative. Right? This happens if the satellite is just above the Earth's atmosphere. So if it's just above the Earth's atmosphere, there's some air there. The satellite will have some air resistance there, so it will do work. So the total energy becomes smaller. That's what it means. Right? Total energy becomes smaller. You move to a smaller radius. So very soon, it will speed up as it go to a lower orbit. Speed up, or we call it spiral to the surface of the Earth. Very soon, the kinetic energy will start increasing. Total energy will start become smaller and smaller until it fall back to the Earth. Okay, that's the application. Right? They're just using this formula, that's all. Right? R smaller, kinetic energy increases or Speed of satellite increases. Right? R smaller, this is more negative. Same, total energy becomes more negative. That's all. Larger value, R smaller. Okay? Either you can use the graph to help you or use the formula to help you understand. Right? Lower R, okay? This is formula. Lower potential energy. Right? Total energy decreases. Lower R, potential energy becomes more negative, decreases. Right? Speed will increase. Lower R, right? Or kinetic energy increases. That's all. Either use formula to help you understand or draw the graph to help you understand. Anything not clear?
No, okay, I need teacher talk very fast, but I need time to understand, so I'll ask you later, I guess.
You should be revising all this already. Exam is coming.
Yeah.
And you want to come
Yes.
for lecture only. You don't want to revise yourself. That's the problem with you. You don't want to learn yourself. That's why it takes so long to teach you. It's just like teaching you from beginning. Right? So where the satellite moves to higher orbit, you should be able to interpret from the graph. Kinetic energy decreases. Right? For satellite to move to a higher orbit, work has to be done to increase the total energy. Right? Total energy is here. Higher orbit, you want to increase to a higher energy. So total energy, you must do work from the graph. Right? Total energy becomes here now. That's the total energy. Potential energy is down here. That's why you need to do work. Okay, so this one just summarize for you. Same thing. Right? Know how to read the formula. What does it mean when the R is become larger? Or look at the graph. Same thing. Both of them explain the same thing. Okay, what's the answer for this one? Yep. What's the answer? Examiner sometimes can play with you all, checking whether you all understand what is going on.
The answer is C.
Right? Remember 4 meter. So it's uniform field. No need to go and work all the formula. Uniform field. Answer is C. Right? G is your 10. Gravitational field strength. Gravitational force is mg. Right? Or mass and acceleration. 2000. Okay. This uniform field. How about this one?
Yeah, go back again, sir. Sorry.
Say again.
Go back again. The previous slide. So what do you meant by 4 meter no need to do anything? I don't get it.
This one gravitational field strength, huh?
Yeah.
The same as acceleration due to gravity.
Yes.
That one is just 10. Yeah?
Uh-huh.
Just testing whether you understand the physics, that's all. Then the force is mg because it's a uniform field. Mass and acceleration. Mass is 20. That's the acceleration. That's all.
Now how come the 4 meter doesn't do anything?
What small Newton, what are you talking about?
Now how come the 4 meter doesn't do anything?
Okay. 4 meter is just to a distraction only. It doesn't come inside mgh. If you want to calculate potential energy, it's mgh, but they didn't ask you to calculate that. Yeah. Sometimes they add information in just for you to distract you. See whether you understand what's happening. Some students will just use the formula GM over R squared. Right? You are wasting your time if you use that.
Only they give 5, then only you have to use lah.
Uniform field, you just use mg, or for one you use g. Want to use f equals to gmm over r square. Can get the same answer, but it take a longer time.
Yeah. Okay.
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 What's the answer for this one?
C. The answer is C.
C, is it?
Wait. Donkey. The answer is donkey.
Okay, basically we are just using this formula, Newton's law of gravitation, right? And call the weight as the force as W as the weight. And we're just using this formula. This is W. Right? The mass is constant. So we take the variable to the other side. R is the one that's changing. Right? That distance is changing. So it's W R squared. Right? So the first W at the surface of the Earth, radius R is this one. And then you move it to height 6R. 6R plus 1 is 7R. So that becomes your W1. And then you square that and simplify it. Okay, R and R will cancel off. Right? R square and R square will cancel off. 7 square is 49. So you take 49 across there. So answer is donkey, correct? Okay, we'll stop here. Only got escape velocity. So we see you on Monday at 3 o'clock. You have to review yourself. If not, I have to spend time, you are paying me to teach you again. All the things I'm supposed to just review with you, but it looks like you have lost completely what I've taught you last semester, last term. So you're wasting your time, wasting money. Okay, you stop here. Anything else you want to ask? Yep. Anything else you want to ask? No, then we'll stop here for today. Yep. Anything else you want to ask? You got question, you can ask me, no problem. I will answer you throughout the whole week. So if no question, we'll have you stop it for today. Finish for today.